techniques of integration. And now we are moving to applications, which is a word that's not very descriptive. We'll try to find as practical ideas as possible and solve them with integrals. But ultimately, what we're talking about is primarily still illustrations of the idea of the integral. So whether it is you think about illustration or applications, these are the two main ideas. And the one, once again, the original application of the integral, in calculus in general, it is determining the location from the velocity. Okay, so that's what Newton did, and he had an actual extra step, if you might remember. In physics, you know the forces. Forces give you acceleration according to second law of Newton, right? From those accelerations, you determine the velocity. So acceleration is the rate of change of your velocity, okay? And then from velocity, once again, you determine locations. But so it's a two-step procedure, and each step is this. Each step is integration. So you going in reverse. So from location to velocity, that's differentiation. From velocity to acceleration, another differentiation. Or in practical physics applications, you go in the opposite direction. Okay. So that's the number one idea. So if you imagine you see concepts about integration, you think in terms of motion and interpret them accordingly. The mathematical interpretation, which also goes back to Newton, at least in part, is that the integral, definite integral, is the area. Okay, so displacement for if the function represents the velocity as a function of time, and here we have a purely mathematical idea that if you draw a graph of a function on the xy plane, then the integral is the area under the graph. Okay, so which one is more important? It's hard to tell. But they're not, as far as applications are concerned, the first one is more important. Why? Because you can easily step away from physics and motion applications to anything that, as long as there's change, as long as something is a function of time. So if you have a function of time, that's x, and then y does not have to be a location in the literal sense. Okay, it could be, for example, temperature depends on time, and then you explore the rate of change of the temperature, or the and vice versa. And or it could be pressure, it could be prices, the stock market, how they vary. Everything varies with time, and everything, if it varies, then there's a change, then there's a change, that's the derivative. If you go backwards, you have your integration. Okay, so as long as there is any kind of process developing in time, then you can always just think integral as displacement. So if you know how fast you're changing, then you're going to know where you're going to be next time. Okay, so that's number one. But the area is more visual, obviously, and so we'll coming back to that, and we already did some interesting stuff with number two, and that's the area of the circle, which is we were going to look at that right next. There is a little bit of a contradiction between these two interpretations. If you think about it, the area is measured. What's the unit of area? The unit of area, what is it? So you have a 10 by 10 rectangle. What's the 10 feet by 10 feet rectangle or square? What's the area? 100 feet squared. That's right. So square feet are the units, right? And then now we're talking about that's the area. That's the only way to do it, and that's if you look at the Riemann Sums, that you will end up with feet squared, right? So you have the width of the rectangle and the height, and feet times feet, you have feet squared. And now look at the number one right there. So what are the units of the integral in number one? It is the displacement. So what's the unit? Unit, location, displacement, what's the unit? That's distance, so it's feet. So as you can see, these two things don't really overlap well. Why? Because once again, if you want to speak of the area, then your x-axis and the y-axis are measured, say, in feet, and then you end up with feet squared. However, if you do any kind of motion, then you have what's the unit of the x-axis? It's time, so it could be seconds. It could be seconds, and then but the velocity is measured in feet per second. Okay, so if it's feet per second, then when you multiply, you end up with feet. Okay, that's how it works. That's really not a calculus issue, but it is interesting how different things have different interpretations. So we'll do both, obviously, and right now let's just do something very simple with the areas. So the area, the question I want to deal with again is the issue of the area of the circle. Okay, so we did it satisfactorily. There was really no problem with the way we did it. But well, we did it on the first day of class. So let's go back. We did it with a spreadsheet. Remember this? So it's an approximation. Let me just show you what we saw here. So H is so we did half of the circle. It doesn't look exactly like a circle, stretched out a little bit, but that's just the way Excel does it. So between -1 and 1, we created how many steps? Probably it appears to be 40 steps. Okay, so 0.05 is the step of the width of those rectangles. Okay, and these are the steps. That's this is the column. The next step is to find the x's. So starting with -1 and ending with 0.95, so all the way through. We are picking left and in each of the intervals. Then we did over here, we did the y's. Here's the formula. Remember the formula? Naturally, the square root of 1 minus x squared. Okay, so that's the column x. I'm referring to the previous one, as if you can read this, RC minus 1. RC minus 1 is reference to R, same row. C minus 1 means previous column. Okay, so you can see it if I highlight this. You can see, I did highlight it, so you can see how the blue one, the blue rectangle, blue cell on to the left is where the x value is stored. Okay, so I'm computing y's. As you can see, y's run between start with 0. That's the 0 we're referring to. So in fact, there is one extra bar here. You just don't see it because its height is 0. Okay, but it's there. Okay, and then it goes on and on and on. In the middle, it reaches height of 1. That's over here, and then go on and then all the way down to 0 over here. Okay. So then I did the areas of what? Of these bars. I simply multiply height by the width. So the width, I subtract those two, the blue one minus the red one in the x column, and then multiply by y, which is the y column. Okay, by 0.031. So I have the area. Once again, I start with 0, close to 0. Then in the middle, I reach the higher point. It doesn't matter. At the end, I add them together. So this is the value. I add them together. Okay, and this is the end. You see, it highlighted the whole column, and the end result, as you can see, 1.56423, which is close to the exact value. The exact value on the right is pi over 2. Okay, so that's what we did, and that's based entirely on calculus 1. So let's make it one step further. Okay, so let's see. So let's say this was half the circle. And so this one will be full circle. Why do I want a full circle, even though with our computation were totally satisfactory? Because well, we did a half of a circle. So we used the special property of the circle. So half was enough. It was this symmetry. So half the circle, I cut it in half, and I know the area of the top will be equal to the area of the bottom. But in general, you can imagine that you have some more complex regions, And the problem is I cannot represent this region in the form of as the area under the graph. So that's what we know about integral. As you can see, it is the area under the graph. Okay, so it worked out for half circle. For the circle, it won't work. And in general, we do need something else in order to represent regions like this. And so let's do, as an example, we'll take the same idea and just do the full circle. Okay, so and we'll just do the full circle. Okay, so this is, we have the same as before. Now what I'm going to do is I'm going to build the lower half. I'm going to build the lower half to begin with, and then we'll see. So there won't be two y's. There will be not one y column, but there will be two y columns. Okay, so this will be upper, and there will be another column for y lower. Okay, so I will insert here a column. Okay, so this one will be, this one we already have. It's the same, y upper. Okay, and now here I put y lower. Okay, so the formula is similar, but what's the relation between the two formulas? So I have my circle again. So this one that I have used is 1 minus x squared square root, and this is what? So this one, and I'm doing the other one, this one. What's the formula? Negative square root of 1 minus x. Okay. So so I'm going to use this formula. So no, I'm not trying to do any. I'm not trying to take shortcuts. And we did because we didn't have any other tool. But now we want to develop something that will work for any shape, just like that one, for example. So I'm going to do the lower one. So here I will write the same formula. I take the same formula and just copy it, and then I'll just have add a minus sign. Okay, so I add a minus sign here. So this one is equal, same. I paste it here, and I'll insert a negative sign over there. I can see negative sign. Right, negative sign. Okay, so as you can see, the value is negative. Hold on a second. That's okay. Yeah, let me fix it like this. Okay. Okay. Now I'm spreading it down. Spreading it down. Okay. Let me make another copy of this. Maybe here. Okay. So I'll change the data from the upper to lower. So just select data. Okay. And I'll pick lower. I'll pick the lower half this time. Okay. Okay. All right. So you see what happens. So this data refers to y upper column, right, over here, and the second one refers to y lower. Let me mark it again. Y lower column. Okay. So as you can see, I have the full circle now, and if I move them a little bit around like this, you can see together they form a circle. So okay. So now I don't want to. Once again, I don't want to do the. I don't want to add two together, but rather what I'm going to be doing is I want to have the look at one bar at a time rather than two bars like this. I'll have one bar all the way through. Okay, so then what is the area of the bar? The width is the same. What's the height? Look at the row. Look at the row. Look at each row. It gives you the lower end of that bar and the upper end of the bar. So what's the height? So, like I said, the first parenthesis here, that gives me the width. Okay, so we have to take care of that. Over here, I still have my formula, which is not right. It gives me only the upper end. So, to get the full length, what do I do? What do I do here? One location, another location, what's the length? The height of this? What? It ends up to be 2, yes, but I don't want to do 2 because it is just a purely coincidental that we're dealing with a circle that have the symmetry. So indeed, the height of those bars above and in the first diagram and the one below are exactly the same. So I could just multiply by 2. I just don't want to do it. I want to subtract. So I have 2 locations. They are given to me, and I just subtract this minus that. It gives me the height. Okay, so so that way we can continue on with. What happened here? Okay, so okay. Parenthesis minus this one. Okay. Okay, so once again, I multiply the width, which is the first parenthesis, times the height, which is the second parenthesis. Okay, so as you can see, indeed it got multiplied by 2. If you can just see it. See, 1.561, 0.303122. So it's multiplied by 2. It's but it is a coincidence more than anything. Okay, let's spread it down. Okay, so and then the total is the same. As you can see, the exact value should be pi. The total area of our unit circle is pi, and you can compare these two numbers. At least the first 2 digits match, and the last one, and then the third one is slightly off. So we were pretty close to the truth. And once again, these are all the data. X's, we have X's, which is the input variable, and that input variable is recycled for the output variables. So y upper gives me this, and y lower gives me that. The two different functions, different formulas. But the way we continued on, we looked at the difference between those 2 locations, and that gave me the height of the bar. So I multiply with times the height, I get the area in this column over here, and then I added them all together, and I have 3.12, almost 3.13, which is fairly close to pi as expected. Okay, so let me do this with just writing. I mean, we have some encouraging results. Let's just write it out what I did more exactly. So okay, so I have then I have my a partition of my interval between -1 and 1 into equal intervals, say n. So -1, 1. Okay, 2 functions. F of x is equal to the square root of 1 minus x squared, which is the original one. G of x is from below, even though it comes from the same formula of the circle, right? There's only one formula for the circle. However, once we try to solve for y, what happens? We end up with 2 equations, and we have to deal with them separately. That's what plus or minus does to us. We have 2 functions all of a sudden, and then we treat it entirely separately. As far as plotting is concerned, so we did plot it. Okay. Now, what are the areas? I will be looking at. Let me pick one and say, well, let's say I'm talking about this one. Always the area of a rectangle is area of a rectangle is the width times the height. Okay. If we go with more specific choices, then you might remember that, say, we have pick, let's say pick n intervals of equal length. So the things develop exactly the same way as in the in calculus 1 in the definite integration. So we start with the Riemann sums. So far, I'm not speaking of Riemann sums. I'm just trying to approximate the area. Okay. So pick n intervals of equal length. So it will be then delta x is equal to 1 minus negative 1 over n, or it is simply 2 over n. Okay. So these are my widths. Okay. And then what I do next, now I need heights. So once again, even though everything is developing similar to Riemann integral, I'm not invoking anything yet, and that will be typically the way we're going to be doing it. We face a problem, we try to solve it, and then at the end of this somewhat hard process, we'll realize that after all, what we're looking at is a Riemann sum. I just need to figure out what that function is. But so at this point, there is no Riemann, there is no Riemann sums. We're just trying to approximate. We have a general idea of how it's done. We start with, once again, dividing the integral into pieces. We're slicing our region into thin slices, and then we are computing the area of those slices. Okay, so an integral, so delta x, that's my width, will be 2 over n, and then the height varies. Height varies from location, but let me write the location first. So locations will be locations of where we slice our circle. Okay, so they will be starting with 0, then 2 over n, 3 over n, I'm sorry, that's not 0, that's not right. Locations. So it will be negative 1 plus 2 over n, negative 1 plus 2 over n times 2, and so on. And the last one will be 1. Okay, so we add 2 over n at the time. So this is x naught, x1, x2, and the last one xn. So once again, similar ideas, but we are doing it anyway. Okay, so once again, this will be x naught over here. This is xn. Now let me draw it again. So we're looking at the interval between negative 1 and 1. Okay, so and then we're cutting it like this into as many as necessary. So, but we start with and it could be any number. Okay, so then the area is once again the width delta x multiplied by, which we already know. Well, let me just write it out. It's 2 over n. Okay, so it will be 2 over n. And then what is the height? The height of the rectangle, and as you can see, I marked it with the purple here. That's my slice, going all the way from the bottom curve to the top. Okay. Once again, ignore the width. We don't care. We only care about this part over here. This one. I'm thinking when you do slicing, by the way, the top is curved a little bit, so we certainly should make no mistake. It's not a rectangle technically. This is the rectangle. Okay, so we're cutting off those curvy part, and they ended up with a rectangle. Okay, so the height is here. The height, how do we determine the height? As we know, we need to subtract how far f is from 0 and subtract how far g is from 0. Okay, so it will be simply f of x k minus g of x k. Okay, so let me zoom in a little bit here. So this is xk plus 1. This is delta x. It goes higher, but it doesn't matter. This is our height. This is the value of, this is how high f of xk goes. So there's a graph of f here somewhere. Doesn't matter what it is. And then there is at the bottom, this is g of xk. Xk, this is g of xk. Okay, so this is g of xk. Once again, there's a graph here somewhere. It doesn't matter. It's all an approximation. And then once again, we're facing this area. that we need to compute this area. Okay, with this continues to be delta x, as you can see over here, and the height is what this expression. Where is it? This is it. Right. So this is it. 2 over n. I can also point it out. This is it. So 2 over n delta x is the width, and that expression is the height of that rectangle. Okay, so that is the approximation. It varies with well, that's not the approximation. That's just a single rectangle, and then we have a bunch of them. Okay, so we have to add them together just the way we did in calculus 1, and so the total area of all rectangles, you just add them together. Remember how we write it? So we repeat this expression that I have over here, and remember how we do it? What's the symbol we use?
Sigma.
Sigma. Okay, so sigma over k running from 0 to n, right? So once again, this is, where is it? Yeah, this is, we are running through these. Okay, each of these produces a bar like this, and we have to add them together. So it will be then 2 over n, and then let me just substitute it, f of xk minus g of xk, and that is pretty much it. Okay, so this is that's the formula I use. I use the exact same formula. Let me show you that that's exactly the formula I use, except when you do it with Excel or any kind of code you write. You don't want to one formula. You rather do it step by step. So the way I did it, I computed these two, okay, separately, and then I computed the whole thing. This whole thing, and then I added that together. So in 3 steps rather than in one formula. It's just easier to do that way. Okay, so let me just show this to you again. So x lower is xy. So in fact, I can now name things here. This is G and this is F. Okay, so and then this is, well, in this expression where everything is coming together. So 2 fractions to 2 parentheses, and one of them, once again, is the width. The other one is the height, and you can see in the parentheses that we have subtraction. And then you just add them together, whatever is in that column, and the answer is here, right here. Okay. So that is all good, but it doesn't really. It really solves one problem, and it's actually not that bad, because if you write it this way rather than insisting on a particular representation of the circle and insisting on the circle, then you can. That's what the power of abstraction. I solve the problem for the circle, but in reality, that method apply equally to any other curve. So I could just take this graph, take the situation, and what do I change? I change G and F. Okay, and what do I put there? I could put any number I like. The advantage of this one is that the end result that it produces gives me a number that we can verify, and we can see that the resulting is indeed close to pi. But still, just for practice, okay. Just for practice, let's do it. So I'll do another one. So how about so the circle? Let's just make up some abstractions. So parabola. Say I put a parabola in the bottom and the top. So G is a parabola. Let's say, what kind of parabola do I like? Say maybe upside down. So how about 1 minus x squared? Okay, 1 minus x squared. The parabola upside down like this. So that will be the lower end of my region. Okay, so I put here, so there is no square root. It will be simply 1 minus, like this. Okay, I think this is right. Okay, 1 minus x squared. No, simply let's say simply like this, 1 over minus x squared. Okay, you will see what this is in a minute, in a moment. Okay, so so the region. Hold on a second. What did I do wrong here? Why does it? What did I do here? -1. Why is it? Why is it 1? What? -1 squared is 1. It should be -1. Why is it 1? Well, so yeah, this is what Excel does. So to look at the formula, appreciate that it should not produce 1. It should supposed to produce -1 if you look at the formula. Look, you see the formula over here. So I'm referring to 1 on the left, okay, and so -1 squared gives me 1, then negative sign in front of it should give me -1, gives me 1. Why? What misunderstanding could possibly Excel have here?
What you're exactly squaring.
What?
What you're exactly squaring.
Right, right. So the order of operations. There is a misunderstanding or a mismatch, let's say, between the algebra and the order of operation that we understand in algebra and the way some of the languages such as Excel use. So it actually takes first negative sign and then squares it. Okay, happens sometimes, and I forget about that. That's how it happens. So as long as I put parentheses here, I will be all right, like this. Okay. Okay. What? Hold on a second. No, I didn't do it right. Minus, like this. Okay, right. Okay, you see the difference, right? So it will square it first, and then gives the negative sign to it. Okay. Let's try again. Okay. I know what to do. It is kind of a pain, but I'll have to multiply by -1, literally. Rather than put a negative sign in front of it, I'll have to multiply by -1. It is a pain, but that's what it's worth. Okay, you see the difference? -1 multiplied by the square. That should work. In fact, I don't need parentheses here, probably. Well, I hope I don't. Yes. Okay. So I just have to be aware of these things. Okay, now it makes more sense, right? So it is the area below the x-axis and above this upside down parabola. Okay, and then I could do the same with the y-axis, but I hope it's more or less clear that I'm not putting together these graphs. It was just the way I plotted. Ultimately what I did, I plotted the upper end and the lower end. That's all. And then the computation itself is literally ignores that part, and it is does the height by subtraction. So this is the subtraction right here, which happens here. Subtraction of f minus g. So let me put something here. Okay. Something. How about same without the minus sign? And well, how about I put 2 here? Okay. Okay, so that's the region I'm looking at. 2 parabolas, non-identical parabolas, one above the other, and how does it compute the area? It takes every time takes the height times width, height times width, and on, and add them together. That's what the summation that we're looking at over here is doing. This summation. Okay, the one thing, however, it is easy to overlook is when because we are satisfactorily solved the problem, and there is really it appears there is no need for us to do anything else with it. But always we want to connect what we have done to something, what we have done now to something that we did some time ago, and the idea is to connect it to the Riemann sum as well as the Riemann integrals. Okay, so Riemann sum has only one function. Okay, so this is not the Riemann sum of f, nor it is the Riemann sum of g. Okay, however, one thing to observe is that is certainly we should make that step, and that is how about we break these two? This sum we break into two, right? So well, let me just write it out. So it will be two summations of the exact same kind, but one for f and one for g. So it will be 2 over n, which is simply the width, f of xk, minus 2 over n, g of xk, k from 0 to n, minus 1 actually. Okay, now what are we looking at? What are these two? Here they are. If we do split them, then the area at the top minus the negative area at the bottom will give me the total area. Okay, so in other words, so that's the geometric meaning of these two terms. It is the difference of the two areas. However, more importantly, these areas, these are two Riemann sums. You can see it from this picture over here as well. So what I did is I just concentrated on this. This is the first term. Where is it? Here it is. Just the upper part of my rectangle is right there, and it is the Riemann sum of f. That's all. So it's a Riemann sum of f, and this one is of g. They actually end up adding together because because g, at least in the picture that we have, g lies entirely below the x-axis, and that's why it adds the positive part to the area and gives you altogether gives you like you add. It seems like you adding together two regions. But in reality, it doesn't have to be this way, and I can show you with Excel once again. What if I want to, I mean, this is a very special case when the graph of f lies entirely above the x-axis, the graph of g lies entirely below the x-axis, and then we add them together. Okay, so that is very easy. But what if they both lie above the x-axis? It doesn't really make any difference. So let me show what I have in mind here. So let's change the lower graph, and I'm going to bring it up by 1. Okay, so same parabola upside down, but I'll bring it up by 1 unit. So in other words, well, how do I do it? How do I bring a graph of a function by 1 unit up? Yeah, so I add 1 to the value of y. Okay, so these are y's. I just need to increase the value of y by 1, so I add 1. Okay, so I just put here 1 plus. Or maybe I put it at the end. Like this. Okay, so let's see what it produces. That's what it produces. Unfortunately, or unfortunately, it is the two graphs now overlap. I don't think. I wish there was a way to fill. I wonder if we have. No fill. Oh yeah, I think it's working. I made the other graph transparent. Okay, so we can see through one through the other. Okay, like this. Okay, in order to, I also want to change the color in order to. Nope. Okay. Different color. Okay, so two parabolas. Why does it look like a parabola? What happened here? What is that? I didn't remember plotting that. What is okay, let me move this. Okay, so what? Hold on, why doesn't it look like a parabola? This definitely is a parabola. It doesn't look like a parabola. You see how it flattens out at the sides? That's not right. We take it and square it and multiply by 2. What? -1 square. What the? Oh, shoot. I see. Yeah, so I messed it up here. Okay, let me start over. So the reference is to the y, not to x, like this. Okay, that will make more sense. Okay. Okay, so that's my parabola. Okay, gives me upper edge of the region I'm interested in, and this is the illustration of its Riemann sum. Okay, so now I take, that's the upper. Now I'm taking the lower, and the lower is already plotted here. As you can see, it refers to the column G. Okay, so, but they are on the same xy plane, and then to understand what I'm trying to accomplish is we overlap them because they are on the same xy plane. So I'll parabola upside down, and this one is, well, it's the same, like this. Okay. Well, you roughly can see the other parabola that goes underneath there, behind these yellow bars. So so then you can guess what's supposed to happen here, considering that we are subtracting the blue area minus the orange area. That's what you see over here. The Riemann sum for F, the blue one, minus the Riemann sum for G, the orange one. Okay, so if we subtract, you can it might be there will be cancellation. Okay, so let me plot this. So you see what's going to happen. What's the end result? But judging by this picture, blue minus yellow. What does it give us? Maybe it's possible, but I wouldn't say necessarily it is the case. We will look at wherever they overlap. Let me move it slightly so you can see. As you can see, wherever they overlap, there are two regions at the bottom, right? They are simultaneously colored blue and orange. Those will cancel. Those that are not colored twice, they will not. And so then the end result will be the blue area that we see to the left minus the orange area above the parabola, plus the blue area to the right. Okay? So that's what the subtraction is, because the orange areas, orange bars, come with the negative sign, so they will subtract it. And that's why, as I said, those little two areas below the parabola and with orange in them will be canceled out. In order to, so as you can see, the area could be negative. It could be negative, could be 0, could be negative. I would say, if I would be judging it, I would say it's negative, right? Wouldn't you say it looks negative, the end result? Right? Because those two blue areas seem smaller than the orange area that remains, right? So it probably will be negative. Let's since what is the meaning of a negative area anyway? So then I suggest to go back to what we started with today, and that is the interpretation of the integral as a displacement. Okay. So what is the meaning of two functions when two functions are present? It means that there are two, say, persons moving. Okay. So we are looking at one person represented by f, and its velocity, or rather its velocity. So over here is this graph is one person moving with this velocity. So the blue graph represents the velocity of the first person. Okay? The orange graph represents the velocity of the second person. Okay? Now the blue area represents the displacement of the first person. The orange area represents the displacement of the second person. Okay, so what's the point here? We will be looking at the distance between two persons. So, well, imagine one person goes this way and the other goes that way. Okay, so then this is f is this person's velocity, and this is the second velocity, g. F plus g. What's the meaning of f plus g? Well, you have two cars, okay, driving in the opposite direction. They have speedometers. If you look at those two numbers and add them together, this is 50, this is 60 miles an hour. What's the meaning of 110 miles an hour in this setting? What does it tell us? No, not the distance, but it is still the velocity. But we are talking about the distance, but we start with the velocity. So once again, 50 and 60 to get 110 tells me how fast they are moving away from each other. 110 miles an hour, they're separating from each other. And then, once again, if we want to know how much the distance has become between them, what do? You take that number and integrate. Okay, so over there, we will have every row will represent the location, the velocity, one velocity, the other velocity. Okay, one velocity, the other velocity at the next moment. So the meaning of this number will be the period of time multiplied by the combined velocity. Okay, that will tell you how far during that moment of time they have separated from each other, how far away they move from each other. Okay, so that also can certainly happen with negative or positive velocity. In that case, we still take into consideration the possibility that they are moving in the same direction, or in the not necessarily in the opposite direction, maybe in the same direction, or maybe they're moving toward each other. That's another possibility. So, well, yeah, you just want to talk about two cars driving away from each other because it just sounds more positive than this, because But the question is actually very practical, because how hard they are going to smash into each other. Okay, so we'll just continue next time.